In this video, we are going to see another application of the section formula and also solve a quiz where we want to prove that a circumcenter of a triangle ABC is given by sine of 2a, so twice of angle A multiplied by position vector of A plus sine 2b to position vector of B plus sine 2c into position vector of C divided by sine 2a plus sine 2b plus sine 2c. Okay, before we go there, let's define what do we mean by circumcenter. Circumcenter is a perpendicular bisector of an opposite side. So if I draw a perpendicular bisector, such that BP is equals to CP, CR is equals to AR, and AQ is equals to, but if AQ is equals to QB, so the perpendicular bisector will meet at a point which is a circumcenter of a triangle, one single point. So a circumcenter is concurrent or congruent. So we can, circumcenter is concurrent. We are again not going to prove the concurrency property of the circumcenter. Again, we are going to assume this in this particular video, but we will go ahead and prove and find out the position vector of circumcenter. Okay, let's prove. So we have a triangle ABC. O is a circumcenter such that OP is perpendicular bisector of BC. OR is a perpendicular bisector of AC, and OQ is a perpendicular bisector of AB. Right? So before we go there, let's look at some of the properties of a perpendicular bisector. So if you are line segment AB and there is a point P, so that AP equals to PB, is a perpendicular bisector. Then what we can prove that if I take any point, so O1, and if I draw a line segment from that point to the opposite point of the line segment which it bisects, then AO is equals to OB. Similarly, if I would have drawn any other point on this line segment, then AO1 equals to O1B. Right? So let's see. Let's say triangle AOP. We can say that AO square is equals to AP square plus OP square, Pythagoras theorem. AP square is nothing but BP square, because AP is equals to BP, plus OP square. So if I apply a same Pythagoras theorem in BOP, this is nothing but OB square, and therefore AO is equals to OB. Right? So if I look at any point on the perpendicular bisector, that line segment to that point will be equal. So what does that mean in our triangle. So this point O lies on the line segment which bisects line BC. So if I draw this point, and this point, so we'll have OB is equals to OC. Similarly, OQ is the perpendicular bisector of AB. So if I join this point, so OB is equals to OA, and therefore OA is equals to OB equals to OC. Right? So this is equals to this equals to this. Great. So what we have proved is OA is equals to OB equals to OC. What does that mean? That means if I draw a circle joining point A, B and C, then O will be the center of that circle with OA, OB and OC as the radius, right? So that's why point O is called a circumcenter of a triangle, because we can draw from that, assuming that as a center, we can draw a circle which will be a circumcircle to triangle ABC. Right. Now let's look at another property. So if you have a circle, right, and then you have a segment, this is center, which is the center O, then by a property of a circle, if this angle is theta, this angle will be 2 theta. Right? So by property of a circle, any chord or any which includes an angle on the circumference of the circle would have an angle which is half of the angle which it has it on a center. Right? So we'll take this property in solving our problem. So by this property, this angle so angle BOC is OA, angle AOB is twice of this angle, 2C, and angle AOC is twice of this angle, 2. Great, let's move ahead. Right, so we have proved angle BOC is 2A, AOC is 2B, and AOB is 2C. So now we can use this to prove, to come to an orthocenter of a triangle. So first, I think if you know, if I extend this point and call this as D, right? So if I find the position vector of D, let's first find what is position vector of D. So we know this angle as 2B, so 2C. So this angle is 180 minus 2C. Similarly, this angle is 2b. So this angle would be 180 minus 2b. So triangle BOD, if I apply a sine law, then sine of angle 180 minus 2c upon sine of this angle, let's say this angle ADB is theta, sine of theta is BD by opposite angle side OB. Similarly, in triangle COD, we can say sine of 180 minus 2b upon sine of this angle, which is 180 minus theta, is equals to opposite side as CD upon OB. OC. Right? So what does that mean? This will give me sine 2c upon sine theta equals to BD by OB. Sine 180 minus theta sine theta, and this will give sine 2b upon sine theta as CD by OC. I can replace by OB. Right? So if I divide this equation, this equation is 1 and this equation is 2. If I did equation 1 by 2, then I would get sine 2c by sine 2b is equals to BD by OB. Sorry, BD by CD. Right? So BD by CD is what we have. So if I now apply so we have this. So if I now apply a section formula, that will give me a position vector of T is a ratio of BD, or sorry, the ratio of CD, which is sine 2b, into the opposite vector beta vector plus sine 2c, which is this ratio BD into gamma vector upon sine of 2b plus sine of 2c, which is D vector. Okay, so we have proved D vector is sine 2b into beta vector plus sine 2c to gamma vector upon sine 2b plus sine 2c. Great. In order to get AO vector, if we able to find out AO by OB, we'll be able to find what is the position vector of A. Okay, so this I leave up to an audience to prove that AO by OD is sine 2B plus sine 2C by sine 2A, right? So this this would imply O vector is equals to sine 2A to alpha vector plus sine 2B plus sine 2C to T vector, which is sine 2B beta vector plus sine 2C into gamma vector upon sine 2A plus sine 2B plus sine 2C. Right? I'll give you a hint. You can use that this angle BOP is equals to angle A. Use this hint to prove this. Great. So we have now seen 4 applications of section formula. Next, we'll jump into the new concept, which is vector products.